everyone, welcome to the channel Statistica Hub. So let's continue with our topic system of linear equations. Okay, so now we'll see non-homogeneous system of linear equation. Non-homogeneous system. So non-homogeneous system is of the form Ax is equals to B. Okay, and the system Ax is equals to B is consistent. This system is consistent, or you can say that it has at least one solution. Okay, has at least one solution if the rank of the augmented matrix, that is AB, is equals to rank of A. Okay, and the system is said to be inconsistent, that is possess, that is it has no solution if we have rank of the augmented greater than rank of A. Okay, in this case the system is inconsistent. Okay, and the third case is if we have rank of augmented is equals to rank of A, and that is equals to n. Okay, that is equals to n, that is we are saying that it is equals to the number of unknowns. Okay, then in this case the system has a unique solution. Okay, as it has a unique solution, so it is this consistent. The system is consistent, and the unique solution is basically x is equals to A inverse B. Okay, and another case is if we have rank of A is equals to R, and which is equals to the rank of augmented, but this R is less than the number of unknowns. Okay, in this case too the system is consistent. Okay, but it has infinite number of solution. Infinite number of solutions. Okay, so now let's just look at these four situations here. So we have this format of Ax is equals to B, which is non-homogeneous. Okay, and we are saying that the system is consistent or has at least one solution if we have the rank of the augmented matrix AB equals to the rank of the A. Okay, now we can also frame this condition like this, that we have this system Ax is equals to B is consistent if and only if we have A transpose U is equals to 0, that is B transpose U is equals to 0. Okay, so you can see it like this, that if we have Y as the solution, okay, then we can write AY is equals to B. Okay, and we are saying that A transpose U is equals to 0. Okay, which implies B transpose U equals to 0. So let's just check that B transpose U. We are saying that AY is equals to B because Y is the solution of this system. Okay, what is my B? B is AY, let's transpose into U. Okay, we can write it as Y transpose A transpose U, and this is the required condition that we have taken, that A transpose U equals to 0, and that this will be equals to 0, and our whole B transpose U will be equals to 0. Okay, so this is how you can say that the system of non-homogeneous system, the system Ax equals to B is consistent. This is the consistent, this system is consistent if and only if we have A transpose U is equals to 0, which implies B transpose U equals to 0. Okay, and the second condition which we have, the second form which we have, the system is inconsistent, that is it has no solution if the rank of the matrix is less than the rank of the augmented matrix. Okay, so you can also say it in this way, that the system is inconsistent. The system is inconsistent if and only if there exists U such that A transpose U equals to 0 and here B transpose U is not equals to 0. Okay, in the consistent criteria we have said that A transpose U equals to 0, which implies B transpose U is equals to 0. Okay, but in the inconsistent condition we have said this, there exists a U such that U is the solution for this matrix. Okay, so we can write this A transpose U equals to 0. So we have A transpose U is equals to 0, the same condition which we have taken here in the consistent form. Okay, so so A transpose U equals to 0, but in this case the B transpose U is not equals to 0. Okay, this is the inconsistent form. Okay, and another for the unique solution, if we have the rank of the augmented matrix equals to the rank of the matrix and which is equals to the number of unknowns, then we will have a unique solution, that is x is equals to inverse b. And if we have the rank and augmented matrix rank are equal, but this r is less than the number of unknowns. Okay, in this case we will have a consistent solution, but they contain infinite number of solutions. Okay, now in this we will have n, we will assign n minus, we have n minus r variables and we will assign some values to them. Okay, remaining n minus r variables like any value like a b c d, any constant. Okay, okay, any value we will assign values to them, and remaining r variables can be represented in the linear combinations of those n minus r variables. Okay, for the infinite number of solutions. Okay, like we have done in the examples too. uh, the one which have pivot elements, we take them as the pivot elements. Okay, and the one which do not have pivot elements, they are free variables. Okay, so we write the elements of the pivot, we write the unknowns of the pivot into the linear combinations of these free variables. Okay, that's what we are trying to say in this last case. Okay, so let's talking about the solution of the consistent non-homogeneous system. Okay, talking about the solution space of this. So the solution space of non-homogeneous system do not form a vector space, because for a vector space to be for a system to be vector space, it has a zero zero vector, that is it should have 0 0 0 0 0 as its solution. But the 0 0 0 0 0 is not a solution in the non-homogeneous system, so it does not have form a vector space. Okay, so this is the note point here, that solution of consistent non-homogeneous ax is equals to b do not form a vector space, because 0 vector is not a 0 0 0 is not a solution in this case. Okay, so we have also seen the criteria of the uniqueness, unique solution too, that when is our non-homogeneous system is unique too. Okay, now there is a important theorem, okay, which said that let v naught, this v naught be a particular solution. Okay, particular solution of this ax is equals to b. Okay, and let this w is the general solution, general solution of ax is equals to 0. Okay, then the following is also is then the following is a general solution of ax is equals to b, that is u is equals to v naught plus w, that means v naught plus w, where w belongs to w solution space. Okay, so what we are saying here this, that v naught is a particular solution of this non-homogeneous system, that is ax equals to b, and we have w which is the general solution of the homogeneous system of ax is equals to 0. Okay, then the sum of these two solutions, that is v naught and w, is the general solution of ax is equals to b, that is non-homogeneous system. So here u is basically obtained by adding v naught to each element in w. Okay, so if we look into the geometrical representation of this, let's consider that w is actually a line. Okay, W is a line and we are adding each element, we are adding V naught to the each element of W. Okay, so let's just say that W is a line which is passing to the origin like this. Okay, this is W. Okay, then when we add each element, V naught to the each element of W, this line will be like this, which is V naught plus W. Like here, it just shifts to like this. That means these two lines are parallel to each other. Okay, similarly we can look this into the R cube. That it means if W is my plane, if W is the plane, then adding each element to this cause the planes parallel. Okay, that means I am saying that if W is a plane, though the origin which is passing to the origin O. Okay, origin like this. Okay, this is the plane which is passing to the origin. Okay, am I drawing it not right? Okay, this is passing to, let's just consider that this is the plane which is passing to the origin. Then U is equals to V naught plus W is a plane. This is the plane V naught plus W which is parallel to W. Okay, this is the W plane, and the another plane which is parallel to it is U. Okay, like this one, which is we have showed this in R square, that we have considered that W is the line, then the V naught plus W is the line parallel to this W. Solution of the general solution of x equals to 0. Okay, now there is a very famous example of this non-homogeneous system, which is determine condition for which system has no solution, second unique solution, and third many solution, infinitely many solution. Okay, and the system is as x plus y plus z is equals to 1, x plus 2y minus z is equals to b, and 5x plus 7y plus az is equals to b square. This is a. Okay, so let's just write this into the augmented form, which is 1 1 5 1 2 7 1 minus 1 a 1 b square. Okay, let's reduce it. So for reducing this, we will apply the transformation. In R2, we will apply R2 minus R1. In R3, we will do R3 minus 5R1. Okay, and that will be 1 1 1 1, and this will be 1 minus 1 0 1 minus 2 b minus 1, and this will be 0 2 a minus 5, and this is b square minus 5. Okay, let's reduce it further. Now we will do in R3, that is R3 minus 2R2. Okay, after applying this, we will get 1 1 1 1 0 1 minus 2 b minus 1, and 0 0 a minus 1, and this will be b square minus 2b minus 3. Okay, okay, so let's just check the conditions here, that talking about the no solution. Okay, so we will have the no solution when we have the rank of A less than rank of the augmented. Okay, that means when we have A is equals to 1, but b square minus 2b minus 3 is not equals to 0. Okay, then in this case we will have rank of A is equals to 2, which is less than 3, because this is actually the rank of augmented, which is rank of augmented is 3. Okay, so this is the condition for no solution when we have A is equals to 1, but this is not equals to 0. Okay, talking about the another condition, which is of the unique solution. So we will have the unique solution when we have the rank of augmented equals to the rank of A, and that is equals to the unknowns. We have unknowns, a number of unknowns 3. So that should be equals to 3. So for the rank of A to be 3, we should have A not equals to 1. because if A is equals to 1, then it should be then it will get 0 and the rank would not be 3. Okay, so A has to be not equals to 1 for the system to be on a unique solution. Okay, so this is the required condition in this case. Okay, and the third, which is infinite number of solution. So we will have infinite number of solution when we have rank of A is equals to rank of augmented, but this is less than 3. Okay, so we will have rank of A equals to rank of augmented if we have rank A is equals to 1 and just solve for the B. Let's say B square minus 2B minus 3 is equals to 0. If we have this, okay, then we will satisfy this criteria that rank of A. Let's just solve this. Will B square minus 3 minus 1 B minus 3 and that will be equals to, sorry, B minus, okay, this would give us B is equals to B minus 3, 3 comma, and that will be equals to plus 1 minus 1. We will have these B is equals to minus 1 comma 3, these two solutions here. Okay, so for a no solution, we have the condition that A is equals to 1 and this is not equals to 0. For a unique solution, we should have A not equals to 1, and for the infinite solution, as this is a condition for the infinite solution, we should have A is equals to 1 and B is equals to 3 comma minus 1, because in this case these two will get 0 and we will have a free variable which is Z in our case, and we have the pivot element which are this. So these are the pivot element, and if we got some value, if these A and B will got some value, then we will find the value of x and y into the linear combination of this free variable. Okay, so this is how you can find the condition for which the system has no solution, unique solution, and many solution. Okay, so now let's see some basics of generalized inverse of matrices. Okay, so talking about the generalized inverses of matrices, generalized inverse of matrix. Okay, so generalized inverse of why do we use generalized inverse of matrix? Because in generalized inverse, every matrix, okay, because there is a very important property in this, that every matrix has a generalized inverse. Every matrix has a generalized inverse, which can be also represented as G inverse. Every matrix has a G inverse, because in previously we have seen this, that and square matrix has an inverse. Okay, and we have taken the generalization here that every matrix which is of any form, of any m cross n form, okay, that can have an inverse which is G inverse. Okay, so let's consider A which is of m cross n order. Okay, then G is said to be the generalized inverse, or you can say G inverse of A if GB is a solution to Ax is equals to B. Whenever Ax is equals to B is consistent. Okay, so what we are saying, that G is generalized inverse of A and X equals to B is consistent if and only if A, G, B is equals to B, where G is the generalized inverse of A. Okay, and the generalized inverse of A is represented like this. Okay, this is G inverse of A. So this is what generalized inverse is, and we can find the generalized inverse of any matrix. Every matrix has G inverse. Okay. Okay. So there are some properties of the generalized inverse. Okay, let's just see them. That we have this matrix A of m cross n, and the generalized inverse of this matrix is A of n cross m. It should have to be n cross m. Okay. Let's just consider that H is equals to A generalized A, and K is equals to A into A generalized inverse of A. Okay, these are the notations here. Then first condition, that A generalized, this is the G inverse of A. Okay, this is G inverse of A. Okay, second thing is that A into A's generalized inverse into A is equals to A. Okay, and the third thing is that H is equals to A's generalized into A's generalized into A is idempotent, and rank of A generalized A is equals to rank of A. Okay, and the fourth property is that K is equals to A into A generalized is idempotent, and rank of this A generalized is equals to rank of A. Okay, and if you talk about the general solution of Ax is equals to 0, then the general solution of Ax is equals to 0, okay, of the homogeneous is I minus H. H is A into A is generalized into A, I minus H Z. Okay, this is a general solution of homogeneous, and where Z is actually the arbitrary vector, any arbitrary vector. Okay, and the other property is that if we have Ax is equals to B, which is consistent, okay, that means it has a solution, then A generalized inverse of A, B plus I minus H Z. This is the general solution in this case, in the non-homogeneous system, where this is what, this is general solution. Okay, where Z is arbitrary vector. Okay, so these are the cases here, that this is the notation, that this is how we represent the G inverse of A. The first second property is that A into A's generalized inverse into A is equals to A. H and K are both idempotent, and their rank is equals to the rank of A. Okay, and if we have a homogeneous system, in this case we have the generalized solution of I minus H into Z. Okay, and if we have a non-homogeneous system, then and that has to be consistent. If this system is consistent, then in this case this is our general solution, that is A generalized inverse of A into B plus I minus H into Z. Okay, now let's see that this A matrix is, if this matrix is of full column rank, okay, then G, that is generalized inverse, or you can also write this. Okay, this is also the G inverse of A. Then G is left inverse of A. Left inverse of A. Okay, we have seen this in the inverse topic. Okay, so if we have a full column rank of this matrix, if we have a full column rank in this matrix, then G is the corresponding left inverse of A. Okay, then if this matrix has full row rank, in this case G generalized inverse of A is right inverse of A. Right inverse of A. Okay, and another case, which is if A is non-singular. If A is non-singular, in this case A inverse is unique. G generalized inverse of A. G inverse of A. Okay, so these are the three conditions, that if my matrix is of full rank, okay, then generalized inverse is left inverse of A. If it is of full row rank, then it is generalized inverse is right inverse of A. And if it is non-singular, that A inverse is unique generalized inverse of A. Okay, now there are some methods to find generalized inverse of A for solving the system Ax is equals to B. So let's just check these method. These methods are actually said the sweep out method. Sweep out method for solving Ax is equals to B. Okay, let's just see this method. Sweep out method for solving x equals to B. Okay, so see this. Let's just consider case 1, where we have the square matrix A of n cross n. Okay, and this matrix is this is the system Ax is equals to B. Okay, and this matrix A is non-singular. Okay, so now this system, I can write this into the augmented form like this, that this is A, okay, and this is the identity In, and this is B. Okay, and then I can first step is this, that I have to write this format, this form into this format, that is matrix A, identity, and B. This is augmented form of AIB. Okay, now after applying the transformation, we have to reduce this. Okay, reduce it to identity, A inverse, and C. Okay, we'll apply operations on the matrix A to make it identity, and we will apply same operation on identity and B. Okay, then we will get our A inverse and C. Okay, so if we have taken that A is non-singular here, okay, then we will reduce it to canonical form. Okay, like if A identity B. Okay, and we are reducing it to canonical form like HGD. Okay, this is the canonical form here. After reducing it to the canonical form, then we will have, okay, so what we are doing is, sorry for that interruption. Okay, so we are taking the case 1, which is a square matrix, and we have this Ax is equals to B form, and where A is non-singular. Okay, and we have written this into the augmented form, and after reducing it, we have got identity, A inverse, and C. Okay, this is the case when the A inverse is unique generalized inverse of A, because it is the non-singular case. It is a case of non-singular. Okay, now we have taken, let's say it is the possible case when our A matrix is singular. Okay, so when our A is singular, then we can write this into the format A identity B. We'll write this into this format, and after reducing it to this format HGD, that means we'll reduce this A matrix to canonical form, and the operations applied on this A, we will apply the same operations on identity and B, and we will get this augmented matrix HGD. Okay, now look into this augmented matrix of HGD. So this is consistent, this system here is consistent if and only if di, that is this di is equals to 0 whenever hii is equals to 0, because we are talking about hii, that means the diagonal elements of this H matrix, the diagonal elements of this H matrix, that is the, this is actually the canonical matrix. Okay, because we are reducing it to the canonical matrix, that's why we are talking about the diagonal element. Okay, so this is consistent if the di, if and only if di is equals to 0 whenever we have hii is equals to 0, that means diagonal elements. Okay, and then the d is actually the particular solution. Okay, and d plus I minus h z is general solution. Okay, and g is the g inverse, of A. Okay, so this is the case 1 for a square matrix, when a matrix is non-singular and when a matrix is singular. For a non-singular matrix, it is so simple. We have just to reduce it and we will get A inverse. Okay, and in the singular case too, we have to reduce it to the canonical form and we will get a generalized inverse. And this is said to be this system is said to be consistent if di is equals to 0 whenever we have uh, our diagonal element equals to 0, where D is particular solution and G is generalized inverse, and this is the general solution of the system. Okay, now let's talk about another case, which is case 2, when a matrix is of A m cross n and the number of rows are greater than n number of columns, that is m is greater than n, and we have this system as Ax is equals to b. Okay, because m is greater than n, we can write this system as A 0 x y is equals to b. Okay, because we have to convert this to the square coefficient matrix. We have to convert to square coefficient matrix. That's why we are writing this into this format. Okay, here if you this is of m cross n and we have m rows, we have m rows which are greater than n columns. Okay, so this zero vector, this zero matrix is basically of m cross m minus n order. Okay, so this is the format here, this is the form here. Okay, now we will form the augmented matrix like A 0 I m b. Okay, A 0 I m b, and we will reduce this to h 1 0 g d. Okay, because how we will apply the transformation here to make this to the canonical form. Okay, we can eliminate this 0 because it the operations on applied on this matrix will be 0 only. Okay, so we can just vanish that. Okay, we can just take it out from this, take this matrix out from here too. Okay, and we will apply same operations for here I m and b, and after applying operation we get this matrix, augmented matrix h1gd. Okay, now what we have to do, we have to partition this final matrix h1gd. Okay, so after partition this matrix, we will get h11 0 0 0. Okay, g1 g2 d1 d2. Okay, where h11 has n rows, Okay, so we are what we are doing is we this is our reduced matrix. Okay, we have partitioned this matrix like this, that h11 has n rows. We'll take all those rows, that is n, we have n columns here, so we are taking out n rows from this matrix. Starting n rows, we'll take these n rows and write this into the format like this. Okay, after writing this into the format, so this system is consistent. Talking about the consistent, see, then this system is consistent if and only if d2 is equals to 0. Okay, this d2 is equals to 0 and ith component of d1 is 0 whenever h11 is 0. Ith component of d1 is 0 whenever h11 is 0. Okay, here d1 is a particular solution. Okay, and the general solution is d1 plus I minus h11z. This is the general solution. Okay, and the g1 is the generalized inverse when we have number of rows greater than number of columns. Okay, so this is the second case. Okay, that's how we can find the generalized inverse for that. Okay, now talking about the third case, which is a matrix A of m cross n, and when we have number of columns greater than number of rows, m is less than n. Okay, and the system is Ax equals to b, and in this case the system can be written as A 0 x is equals to b 0. I can write we can write this down in this format. Okay, and where this 0 matrix is of n minus m cross n order, I think so. It is of this order. Okay, now we will form the augmented matrix. like the previous cases, which is A0, IN, and B0. Okay, and reduce it to HGD. Okay, we will reduce this, and after reducing, okay, so now look at this sum matrix G. Okay, sum matrix G, which is formed by first m columns. Okay, we are talking about sub matrix G formed by first m columns. First m columns is a G inverse of A. G inverse of A. Okay, and this system is consistent if and only if di is equals to 0 whenever hii is equals to 0. Same condition in like the previous cases. Okay, and d is the particular solution, and d plus I minus hz is the general solution in this case. Okay, so there are three cases that we have done now, that when we have a square matrix, okay, and the other is when we have number of rows greater than number of columns, and another case which is when we have number of rows less than number of columns. Okay, in these all cases what we have to do is we have to form a square coefficient of matrix. First step is we have to form a square coefficient of matrix. Okay, so we don't have to do this task in the square matrix because it is already square. Okay, so for making this uh, for making the coefficient matrix into square matrix, we have to add some columns in this case because it has number of rows greater than number of columns. Okay, and in this case for a making of for a making square coefficient of matrix to square, for making a square coefficient matrix we have to add some number of rows because they here we have number of columns which is greater than number of rows. Okay, so first thing is square coefficient matrix. Form the square coefficient matrix and then reduce this matrix. Okay, after forming matrix, write this into the augmented form. Okay, augmented form. After writing it to the augmented form, reduce it to canonical form. Canonical form. Okay, and after reducing it to the canonical form, we have to check the conditions. Okay, we have to check the conditions like if and only if my other, like there are different conditions for the one for these three cases. That is, the common condition is that di is equals to 0. If and only if di, that is di is equals to 0 whenever the diagonal element of this canonical matrix, the diagonal element of this canonical matrix is 0. This is the most important case here. This is followed in all these three cases. Okay, that di is equals to 0 and whenever hii is equals to 0. This is the case of consistency. Okay, and then in all these we will get a format, okay, after reducing it, where we have a d as our particular solution, and the general solution is d plus I minus sz. Okay, and what is that and we get our generalized inverse. So this is basically a simple format, but we just have to maintain the order of the matrix. We just have to remember that whether the m is greater than n, m is less than n. Okay, so by taking into account all these conditions, we have to perform the operations, and we can easily find our generalized inverse by applying these operations. Okay, so this is all about the generalized inverse of the matrices. You can do some examples of these generalized inverse. Okay, so thank you. This is all about this lecture.